Okay, so what is the application of having a weakly reflected ray at an air glass interface? We have these one-way mirrors, which you commonly see in a scene like this, the TV shows. You have the police investigator and the witness standing in one room, looking into another room, trying to identify the suspects. So how does the one-way mirror work such that this witness can see the suspects, but the suspects are not able to see him? Now, how does this one-way mirror work? It's actually made up of a sheet of glass coated with a thin reflecting layer of metal, just like your normal mirror. But let's say, for example, your normal mirror is coated with 100 atoms of silver metal. This one-way mirror is coated with half the amount, that means 50 atoms of silver metal. So instead of reflecting completely, it allows half of the light to be reflected, and it allows the other half of the light to pass through. So for this to work, the suspects are in a room that must be brightly lit, okay, whereas the police and the witness must be in a room that is completely dark. So the light from this room will hit the reflecting surface, okay, and reflects back into the eyes of the suspects. So for them, they only see their own reflection. But at the same time, this glass surface actually allows some light to pass through to this dark room. So it allows these suspects, these witnesses and the police to see the faces of the suspects as well. Okay, so this looks like this. When you have the light source in the lighted room here, the light source hits the glass, you have reflection. So the suspects see themselves, their own reflections. Then some of the light passes through to the dark side where the police and the witness are, and they will have a very clear view of what is outside, that is in the suspect's room. Okay, remember at the start of the chapter, we talked about the swimming goggles at the bottom of the swimming pool appearing to the person looking at it to be closer to the surface of the water than it actually is. So how do we use refraction and ray diagrams like this to explain what is seen? Okay, so when light travels from the goggles to the observer's eye, as the light ray travels out from the water, which is optically denser than air, it bends away from the normal. Okay, it bends away because air is optically less dense. But the eye actually see the light ray to be traveling in a straight line. So you see this image of the goggles above the actual goggles. So the actual goggles is at the bottom of the swimming pool. This is the real depth. But now you perceive and see the goggles at a position nearer to the surface. So the pool also seems to be shallower than it actually is. Okay, so we are going to call this depth the apparent depth, which is less than the real depth or the actual depth. Earlier on, we calculated refractive index n equals to c over v using speed of light in vacuum and speed of light in the medium. Now we can also use another formula, n equals to real depth over apparent depth, to calculate the refractive index for cases whereby the light rays are traveling from your optical medium to air. So from a denser medium, okay, so your real depth is a higher value to a apparent depth which is a lower value. So your n is still greater than 1, just like how you calculated using the other formula. Okay, so refractive index can also be given by the ratio of the real depth of the object in the medium to its apparent depth in the same medium. Same thing, because it's a ratio, n here has no units. One of the phenomena of refraction is bent objects, like the bent pencil that we see earlier on. Okay, so when we have a rod placed in water, it appears to be bent. Why? When light travels from the object or the rod at the bottom here, as it travels, it bends away from the normal when it is traveling from water to air. But our brain tends to tell us that the light rays are traveling in straight lines. So we appear to see the image of the object higher than the actual position. So if you look at different points and you join the rod together to the water and air surface, you end up getting a bent rod here. Okay, another phenomena of refraction is the misperception of depth, where the effect of refraction makes the swimming pool seem shallower than it really is. Okay, so let's take a point O at the bottom of the swimming pool. As light travels from this point to our eye, it actually bends away from the normal when it is traveling from water to air. Okay, so it bends away from the normal, bends away from the normal. But our brain again tells the eye that light rays are traveling in straight lines. So you see this point O's image higher than it is actually at. So this position now, okay, causes the pool to look like it is shallower, with the apparent depth less than the real depth here.